Hello guys, so today I want to give a detailed explanation on Friedel Crafts reactions. It is containing both alkylation and your acylation. So now when do you think Friedel Crafts alkylation works? So the first line if you read, it says that aromaticity or because of benzene stability. Now most of your reactions, right, assume I have a simple alkene. Okay, so I have a simple alkene and then you're treating it with any of your chlorine. So you will notice that the chloro is adding on both sides of the double bond, which means you'll get something like one chloro here, one chloro here. And these kind of reactions, we call it as addition reactions. But in the same place, if I have a benzene, right? So here also I have a benzene with a double bond and try reacting it with any chlorine. Apart from when it is undergoing free radical mechanism or under light or UV, if you notice these kind of double bonds don't react with chlorine to give you addition products. Now that reason is basically because of your aromaticity, which means the pi bond in the benzene is in resonance, which means the pi bond is not available for any of your addition reactions. So that's why we don't have Friedel Crafts, addition reactions are not there, but rather you have your Friedel Crafts reactions for any of your benzene. Now second thing, because they don't undergo your addition reactions, we have another class of reactions which is your electrophilic aromatic substitution, also called as your EAS. In this what is happening is, if you have your benzene now acts like a nucleophile. Okay, so it acts like a nucleophile, which means the incoming electrophile will go attack the nucleophile, abstract one particular thing and the reaction goes forward, which means you can understand that when you only have a strong electrophile, it is able to attack the benzene, which acts like a nucleophile to carry out the reaction. Now, like I told you in the beginning, there are two types of Friedel Crafts. One is your alkylation, the other one is your acylation. Let me start writing a simple reaction for this. So assume you have your benzene, okay, and then I am treating with a CH3Cl. Now because this is your alkyl group, so this reaction is also called as your alkylation. Now you have to treat it with a strong Lewis acid. So this is becoming your Lewis acid. So this is your Lewis acid, which is playing an important role in abstraction of your Cl. And then you notice that the product basically contains your benzene with the addition of your alkyl group. So this is the simplest form of reaction in which you notice that you take your alkyl, whatever is the alkyl, you add it to one of the benzene. So this becomes like your toluene. Okay, so you started with benzene. Now in place of your CH3, you can have your multiple homologous series. You can have your C2H5, you can have your C3H8, you can have any of the other formats, and then subsequently you are going to notice that the alkyl chain is going to get substituted with the benzene. Now if that was your alkylation, then this is called as your acylation. In your acyl, an acyl group is added. So this group is basically called as your acyl chloride, and if I'm adding this part to the benzene ring, then it is called as your acylation. So we can take another benzene. So as usual, you have to take an acyl chloride and then you have to treat it with the Lewis acid, and the product will be your acylated benzene. So you always get a ketone, and in this case it is your acetophenone. So your starting material is a benzene. Now if you look at both of them, because you added your acyl, it is called as your acylation, and if you added an alkyl, then it is called as an alkylation. So how exactly do you think the mechanism works? So let's deal with your alkylation. Assume I'm taking any of my alkyl chloride. So this is your alkyl chloride. I told you that I'm going to treat it with a Lewis acid, which means let me take something like AlCl₃. So you can also take your FeCl3. So if you notice the structure of this looks something like Al, Cl, Cl and Cl. So you know this is slightly your delta negative and this is slightly your delta positive, which means this aluminum it's going to give maximum covalence is +4, which means you'll notice you're going to generate an electrophile from the alkyl, and then on the other side you will be having AlCl4 minus, which means this chlorine got abstracted to the aluminum, which means you first generated the electrophile. So this becomes your step 1 generation of your electrophile. In the step 2, you will notice that there is a benzene, and then you have your electrophile, where I told you in the beginning itself that the benzene is going to now act like a nucleophile, which means this bond is your electron rich bond. So this is going to open up to form a bond to this carbon. So you will notice, so you have like this, and here you have the desired bond. So usually there is a hydrogen attached, so you have your CH3 with proper bond. Now you notice, because this was a homolytic cleavage or your heterolytic cleavage, which means you have a positive sign here, which means in the next step you will notice that the hydrogen is going to come back in, which means you get your product back. So you get back your toluene, which I just described. So what do you notice? So you notice that the most important step was hydrogen coming in and the electrophile being attacked through the pi bond. So this becomes your alkylation. Now in the same place, if I have your acylation, so let me take an acyl, CH3, C double bond O and a Cl. Now again I am treating with a Lewis acid, AlCl₃, okay, which means you notice this is a delta negative, which means you will notice CH3, C double bond O, right, and then you have a plus. So the electrophile is generated, and as usual AlCl4 is there. Okay, now let me take the electrophile. I have my benzene, and I'm going to treat it with my electrophile C plus, which is having a C with a CH3. So this bond is going to go there, attack it, and as usual you will notice that the mechanism is almost the same. So you have your C double bond CH3, in which you have another hydrogen and a positive carbocation. So in the next step this comes back in, so you will notice you are going to get back your acetophenone. So you have your acetophenone. So now these two becomes your general mechanism for most of your alkylation and acylation. Now what do you think is the limitation of this? Or let me take another case in which you will notice I have already given a benzene, and to this I am adding a meth eth prop. So this is your N-propyl. So most of the times, most of the students will write that the product of this is going to be something like this. So they will think, oh, I have a propyl ring, so let me attach meth eth prop, meth eth prop. But you know, you should understand, this product is not the product for this reaction, but rather this is a wrong one. So this becomes your wrong one. So what exactly do you think happens? So let's take the intermediate, or this. So let's take 1, 2, 3. So 1, 2, 3, and then you have your chloro. Like the way I explain in my mechanism, let me take my Lewis acid, let it be AlCl₃. So you will notice that this minus is going to come here, which means you will notice that the carbocations look something like this. You have your 1 carbon, 2 carbon, and your 3 carbon, where there is a plus. But you should understand that this is your primary carbocation, whereas this is your secondary carbocation. And we should know that there is a shift in this position. So this is also called as your hydride shift, where now the carbocation has been shifted to the secondary position. Now this becomes my intermediate, which means you should understand that when I take my benzene, okay, so I'll take my benzene, okay, now I have my carbocation in this way, which means you should understand, so this will go here and your product will look something like this. So you start with the N-propyl, whereas you end with an isopropyl. So this, you know, is your cumin based product. So now you should understand this becomes your limitation of your Friedel Craft, where you should always check whether your product is primary, secondary or tertiary intermediate. Based on the stability, you have to shift your carbocation and then finally react with the final one. So this becomes your one case in which students get confused. So the final one, what is the limitation, the basic limitation of your Friedel Craft? So if you have written the first one, that there is something called as your polyalkylation, which means assume I have a benzene and you thought I have a benzene and you thought, okay, if I do my CH3Cl in presence of my Lewis acid, so you're assuming that, okay, let my product be toluene. But in reality, what happens is, because this is an electron donating group, which means it will activate the ortho and para, which means after a point you will notice that methylations can occur multiple times, and this is called as your polyalkylation, which means that is what I've written. And in the same case, assume you have some electron withdrawing group, something like this. Now, if I have an electron withdrawing group and then you're trying to activate by doing your EAS to give you an alkylated product, this reaction will not work. So this reaction will not work. So you will notice that if you have a deactivating group such as NO2, SO3H, CN, CF3, these reactions will never undergo your Friedel Craft alkylation, and if you have your normal alkylation, it will always undergo polyalkylation. These two becomes your drawbacks of Friedel Craft. Otherwise, this is a very popular reaction in your chemistry, organic chemistry. So thank you. I hope you understood. So let me be back for more interesting videos.